Promise in class, I was going to make a video on the Cramer-Rao lower bound. Okay, so I want to welcome you to the Cramer-Rao lower bound. Just like what I said in my last videos on my previous videos on the score function, the facial information, they are all related to the Cramer-Rao lower bound. But you know what? Because before moving forward today, I'm actually going to tell you the significance of what we're doing now, the camera lower bound. Of course, I told you the other time that if you understand, if you know the intention of what is behind the scene, okay, if you understand what is behind every notation, every symbols, every statistical models, of course, you're actually going to appreciate what you're learning. So what I first want to do now is to tell you significance of the Cramer-Rao lower bound. Okay, I'm actually going to say this concept is fundamental, okay, concept in statistics, and I'm actually in signal processing, because it provides a lower bound on the variance of any unbiased estimator of a parameter. Of course, whenever we want to figure out the value of a parameter, we normally take a sample, and the moment sample is involved, parameter estimation is going to be involved. And when parameter estimation is involved, we're actually going to use an estimator, okay? So the Cramer-Rao lower bound, like I said, the significance of it actually uh, extend across various fields, including economy, medicine, business, engineering, and environment. But I will quickly, what is significance of the Cramer-Rao lower bound? Okay, in economy. Okay, it will help understand the theoretical limits of estimation accuracy, aiding economists in designing efficient models and policies. Okay, particularly if you want to talk about econometrics, where parameters like elasticity of demand or production function are estimated. Okay, the Cramer-Rao band provide an insight into the precisions of the estimators. And of course, the moment your estimators are precise, okay, and that will help to assess the reliability of economic models. Okay, so for economic models to be great, okay, then it means the estimators, okay, are actually, they attain Cramer-Rao lower bound, okay, it makes sense. Okay, when you want to talk about um, you know, treatment, drug development, diagnosis, and treatment planning, I'm actually gonna say, in all of this, we need accurate estimation. Okay, so and I'm actually gonna say that the estimation of parameters such as tissue property or physiological parameter are very essential for accurate diagnosis and monitoring of diseases. So the Cramer-Rao lower bound in medicine actually help in assessing the performance of estimation techniques and guiding the development of more robust and accurate medical imaging algorithm. Okay, so in environment, it helps in understanding the limitations of parameter estimation technique, guiding environmental scientists and engineers in designing more accurate and reliable models for environmental prediction and management. I think this is going to go all the way, okay? So, but what I want to do right now, I want to go into the mathematical principle coupled with the statistical principle, that involve around the Cramer-Rao lower bound. So let me tell you this. The whole idea actually started from score function. I told you the other time. Okay, the score function is a random variable s for one sample size. It's actually gonna be the theta or ln of f of s given theta. And of course, I told you the other time the expected value of a score function equal to 0. I think I walk you through that. And of course, Fisher information for one, for a sample size of one is actually the expectation of, the square function, okay, which is actually, the expectation into d theta, okay, ln f of s, theta, okay, all squared. And alternatively, I can also write a Fisher information, which is a Fisher information. So I can also write that, if I do the second derivative, okay, the second derivative, multiply by, a negative value, okay, they're all going to give the same results. Okay, so, but let me tell you this, for an unbiased estimator, okay, an unbiased estimator is an estimator, okay, where the expectation of that equal to that. Okay, I'm actually going to say, the Cramer-Rao lower bound now is going to be, the inverse of a Fisher information. Okay, so which is going to be 1 divided by Fisher information. And if I'm dealing with a sample size n, so of course it's gonna be for n. Okay. Now, that is a Cramer-Rao, the Cramer-Rao variance. Some of you may be wondering, um, is there any difference between the Cramer-Rao lower bound and the actual variance of the estimator. Okay, so I'm actually going to say there is a difference. So what Cramer-Rao lower bound is actually talking about, okay, in statistical theory, is that we're able to the estimator was able to have obtained the minimum variance possible, okay, within the class of unbiased estimator. You remember the other time in class, I actually said that we deal with uniformly unbiased estimator, and I remember I started from the idea of figuring out sufficient statistic, and I show you how to use a Fisher-Nehmer factorization to figure, to derive a sufficient statistic. And I finally said, if your proposed estimator is a function of sufficient statistic, then I'm actually going to call that estimator, a minimum variance unbiased estimator using the Rao-Blackwell theorem. Okay, the idea of a Rao-Blackwell theorem, if you remember what I said the other time, when the conditional distribution of an estimator giving sufficient statistic. I think the Cramer in 1945 and David Blackwell in 1947, in their paper, they actually discuss the idea of Rao-Blackwellization, a way to transform an estimator, into, a way to improve the efficiency of an estimator. Okay. Now, that is not the only way. We believe that if we identify a sufficient statistic, whether through Nehmer-Fisher factorization or Skeffey-Lehmer factorization, and if estimator is a function of a sufficient statistic, okay, using the idea of our Blackwell theorem, we're actually gonna say that particular estimator, as a minimum variance unbiased estimator. Well, let me tell you that that is not the only way. Okay, what I'm presenting to you today, another way to show that an estimator, okay, as a minimum variance and its unbiased estimator is to show that it attain a Cramer-Rao lower bound. Okay, so how do we actually? I'm first going to show you. You know what I just showed you right now is that the inverse of a Fisher information is a Cramer-Rao lower bound. Okay, it's Cramer-Rao, so which is a Cramer-Rao variance. But uh, how do we show that the variance of the actual estimator, okay, is greater or equal to 1 over, the Cramer-Rao, 1 over Fisher information? Okay, so how are we going to show this? Okay, what you have at the left hand side is the actual variance of the estimator, and what you have at the right hand side is the minimum variance ever. Okay, now if you really want to show this, we're actually going to use the idea of a Cauchy-Squash inequality. Okay, we talk about Cauchy-Squash inequality. Okay, now the Cauchy-Squash inequality actually is, we got expected value of a score function minus expectation of a score function. Okay, and they multiply by an estimator minus expectation of the estimator, okay, all squared, okay, will be less or equal to expectation of x minus expectation of days, okay, squared, then multiply, continue from here, multiply by theta curve minus that, okay, this is according to Cauchy-Squash inequality. Okay, now when you take a look at this guy now, okay, take a look at that guy now. We said the other time expected value of his score function equal to 0. This guy is gonna go to 0, and I'm actually gonna be left with x into theta curve minus expectation of this. Okay, I'm actually going to be left with this. Okay, now less or equal. If you take a look at this guy, that is more or less like a variance of a score function. And when you take a look at this guy, that is automatically the variance of a theta curve. Okay, now when you take a look at what I have here, by the time you multiply out, okay, I'm actually gonna have expectation of this guy. Okay, now squared less or equal to the variance of phase, the variance of a theta curve. Okay, now I want to work on the estimator inside. I want to work on the estimator inside now. Okay, now working on the estimator, I'm gonna clear my whiteboard. Okay, I'm gonna clear my whiteboard. Okay, now when you take a look at that, let me for what we have now, we got expectation of x that, okay, all squared, okay, less or equal the variance of s, okay, and the variance of its theta curve. Okay, now I first want to work on the expectation of this guy, which is going to be integral because that guy is a random variable. Okay, I'm actually going to have this guy then multiply by f of s given theta ds. Okay, so when you take a look at that guy now, okay, when you take a look at that guy now, okay, the next thing that we're gonna have, don't forget your score function is the theta ln f of s given theta for one observation. Okay, so this guy is now going to be, okay, integral. Okay, so that is now, okay, I'm actually gonna have the theta ln f of x theta, that is for the x, then multiplied by that, and I'm gonna have this guy dx. Okay, I think you're following that. The next thing I'm actually gonna have right now. Okay, let me clean this one. Okay, so what I'm gonna have right now, okay, is I want to apply my mathematical sense here. I want to have a derivative of a natural log. Okay, so the expectation of this guy now, okay, is actually going to be, okay, now this is going to be d theta f of s, okay, divided by f of s theta. When you differentiate this guy, then theta cap, okay, f of s, okay, given theta, okay, ds, okay, mathematically speaking, that guy cancel that guy now. Okay, so if that guy cancel that guy, what am I talking about? Oh my God, what am I talking about? The way it is now, I'm actually going to bring the theta out. I'm actually going to have a theta cap f of x theta ds. I needed to take a look at what I have inside here. What I have inside here is expectation of a theta cap. Okay, when you take a look at that, okay, now expectation of a theta cap d theta. Okay, now a situation where the expectation of a theta cap is equal to theta, so which means if it is unbiased, I'm actually going to have d theta, okay, and theta. Okay, differentiating that now, that's going to be 1. Okay, now the moment I got 1, okay, but what of in a situation where I don't get 1? Okay, now what I'm going to do now, there's going to be two scenario situation where the theta cap is unbiased. I'm actually going to have expectation of theta cap. It's going to be theta, and that will lead us to this. Okay, but what of in a situation where that doesn't happen? Okay, I'm going to clean up now. Now, situation where that doesn't happen, okay, it's just going to be d theta, okay, and in a parenthesis, okay, I'm actually going to write expectation, okay, I'm going to write expectation, then I'm actually going to have theta cap, okay, minus theta, okay, and that is going to be squared, okay, in a situation, okay, so that is what we're going to have. Okay, so now let me now say this. Okay, I'm dealing with the unbiased estimator. So this guy is going to be 1. 1 square is 1, less or equal to that. Okay, and the variance of a theta cap. Okay, now finally, okay, when you take a look at what I have right now, finally, okay, so finally, you know, don't forget this guy is the official information that I talked about the other time. Okay, and this is the variance of the actual estimator. Okay, I want to get this, and I'm going to divide both sides by the Fisher information. Okay, so when I do that, this is going to cancel that. Then, when I have 1 over that less or equal to that, then it means if I want to write that, it's actually going to be this 1 over that, okay, for one observation. So take a look at this. So this is how to show that the actual variance of the estimator will be greater or equal to the Cramer-Rao variance. Okay, now situation where an estimator attain a Cramer-Rao lower bound, okay, we're actually saying that that particular estimator is a uniformly minimum variance unbiased estimator. Okay, that's how we do it.